Hello and welcome to Civil Engineering Mathematics A, Program 2. My name is Eric Tune. I'm a lecturer in mathematics at Central TAFE. Before we make a start with Program 2, just want to remind you of a couple of things. First of all, in order to get credit for this subject, you have to be enrolled. So you have to contact your local college and enroll. And the reason is there are assessment requirements for this subject, and there might be some other requirements you have to be aware of. The other thing I like to remind you of is the textbook. Now, mathematics is a doing subject. You have to do it. Watching me doing the mathematics is not going to make you person first in mathematics. You have to do it yourself. And we've got an excellent textbook, and I might just hold it up. It's the book by Eldis and Pentlin. It's called Mathematics for Technicians, and it's written specifically for this subject. And the follow-up subject, Civil Engineering Mathematics B. Now, where can you get that book from? Where can you get more information? Let's have a look at the screen. You can contact West 1 Information and Sales Promotion Center, and the telephone number there is 9229-5252, and of course you can also go to the net. Let's make a start then with Program 2. In Program 2 we cover two different topics. We finish off with our measurement and mensuration, so that's the second part, and then we have the introduction to geometry. In more detail, we look at area calculations, we have volume calculations, then we have some definitions, a lot of things to remember. We do angle arithmetic, that's quite interesting. Then we have some angle problems, and I'll give you at the end an example of a construction in geometry. Okay, let's make a start with area. Now, area, if you can see the definition here on the screen, is basically the amount of surface that is covered by a figure. We use squared length units. So if I've got a small area, I might talk about squared centimeters. If it's bigger, squared meters. And area for land is normally measured in squared kilometers. There's also this special unit called an hectare, which is 10,000 square meters. There are certain formulae for area, and I've got those listed here. For a rectangle, it's simply the base times the height. For a triangle, we take the half of the base times the height, and you can actually derive that formula quite easily. For a circle, we've got pi times r squared, r being the radius, pi being that number 3.14. Well, let's do some problems, easy ones first, and then it becomes a little bit more difficult. First problem here, find the area of this triangle corrected to decimal places. Well, we know that the base there is 4, we know that the height is 3, and so using the formula half the base times the height, I get half times 4 times 3, and that equals 6. Now be careful that you put those units there. This was measured in meters, so the units become squared meters. Next problem, we've got there a combined figure. We've got a circle cut out of a rectangle. We have to calculate the area that remains. We know that the radius is 2 millimeters. First of all, calculate the area of the rectangle, 16 times 6, 96. Then take away pi times 2 squared. Remember, the radius is 2, and if you do that on the calculator to one decimal place, comes to 12.6. Take the 12.6 away from 96 and you end up with 83.4. Now, sometimes you have to use the theorem of Pythagoras to calculate areas, and the example here follows. Here we don't know what the height is of this particular triangle. We have to work it out first using Pythagoras. Now, this is an easy case because we know that these sides being the same length, that will make this side here 2 centimeters, half of 4. Then we can use Pythagoras to calculate the height, because that should be 3 squared minus 2 squared, and then the square root out of that. That becomes the square root of 5. Then I know that the height is the square root of 5. I know the base still is 4. Multiplying it all out on the calculator, I get 4.47. There are other formulae for area, and one important one is Herons Formula. Some people call it Herons Formula, but it's actually Herons Formula. It was one of those Greek mathematicians like Pythagoras who developed this. Very difficult to prove this formula actually. And if you got a triangle with sides A, B and C, then the area can be obtained by using this number S, which is half the perimeter. You add up these A, B's and C's, you take half of that, and then you put it in this formula. It's the square root of S multiplied by S with the first side subtracted, multiplied by S with the second side, and then multiplied by S, take away the third side subtracted. An example follows. Here we've got that same triangle we had before, 3, 3, 4. This formula goes a lot easier because you just add 3 to 3 to 4, you get 10, half 10 you get 5. Then you put that in that formula, 5, because S was 5, and then 5 times 1, 5 times, it's 2 there, and it's 3 there. No, sorry, it is 2 there, and that should really be 2 as well. And so we end up with the square root of 20, and we get that same answer we had before, 4.47. These were relatively easy area problems, and you should practice some more problems from your book. Let's take a small break and then we come back with volume. Volume deals with content. Now there are two types of content. It can be a fluid, and it can also be other material, of course, like sand, for instance. And if you give the units when you deal with volume, then you have to ensure that it's liters when you have fluids, and square length units or cubic length units if it's other material. Well, let's go to the definition of volume. We see that the volume of a solid is the amount of content is contained, and as I mentioned to you, it's cubic length units, except when it is a fluid, then you use liters. And there were those conversions we used in program 1. Important conversions were that 1 liter was 1,000 cubic centimeters, and we've got 1 milliliter to be 1 cubic centimeter. And the other conversion was that 1,000 liters is 1 cubic meters. Quite important to remember that. There are two different types of figures, or solids I should say, that's the technical term. There are the ones that have square sides, or sides that are perpendicular to the base, and there are the figures that end up in a point called a vertex. Now those are generally called pyramids, the ones that end up in a point. And if you have a prism, then you've got those parallel sides, or the parallel ends I should say. And depending what you have, you got different formulae. If you have the simple prisms, then you just take the area of the base and you multiply it by the height. Now, that's a pretty straightforward process. When it's a pyramid, you actually have to multiply the result by a third. So you take 1/3 area of the base times the height. You can actually prove these formula with a subject called calculus, which you might do one day in the future. We've got also a sphere, and that has a special formula involving the r again, and it would be 4/3 pi times r cubed. Well, let's get stuck into some problems. Easy ones first, more difficult ones later, and there's one difficult one there. Here we've got just a rectangular box, 4 by 5 by 3. What would be the volume? You look at 5 times 3 for the base, which is 15. You multiply by 4 to get the height, and the total then becomes 60, and make sure you've got the correct units, cubic centimeters. Let's now have a look at the problem that involves a cone. A cone is like a pyramid, which has got a circular base. And here we've got a base radius of 121 millimeters and a height of 225. Here we've got the drawing of the cone. Remember, it's a 1/3 problem because it's a pointy shape there. Area of the base is going to be pi times the radius squared. We multiply it by 225 for the height, and you've got this huge number. Now, because there are 1,000 1,000 milliliters in every cubic millimeter, we have to divide this number by 1,000 to get the correct answer, and then you have to round it as well to the nearest milliliter. You might have to do that on your calculator at home and verify that that is correct. Next problem, something with a pipe in it. We've got here a cylindrical water pipe that has a length of 5 meters, external diameter of 50, internal of 40. You have to work out to the nearest cubic centimeter what the volume of the material is to make the pipe. Now what I've done here, and then you don't have to do the conversion, this is just one of these little tricks that you pick up after years of doing mathematics. I converted it straight away to the correct units, in this case centimeters. So I changed the 50 diameter to a radius of 2.5 centimeters, and I did the same with the internal radius. Here we've got the length of 500, same drawing as before. Then the area of the base is going to be pi times the external radius squared minus pi times the internal radius squared. We work that out first, and you've got this particular number then, 7.068, and some other decimal places following that. Then we multiply by the height, in this case the length you could say, which is 500, and that comes then to 3534 cubic centimeters. Let me do one more problem on volumes, and that involves a sphere, and it also involves algebra, and that's what you will be studying later in programs 4 and 5. Here we've got a soccer ball, approximate radius there is, or circumference I should say, 60 centimeters. That is the outside edge there. Calculate the volume correct to two significant figures. So you have to know what significant figures means. You have to know what circumference means. Here we've got the soccer ball drawn. We know that circumference is 2 pi r. But in this case we know the circumference at 60, we don't know what the radius is, but if we know the circumference, we know what pi is, then we can work out what r is, and that's where you use your algebra. I'm not going to go through any great detail yet, but you can actually work out from this that r has to be about 9.54 etc., and that would then be in centimeters. Then we know that the volume is 4/3 pi times the radius cubed. So we know what the radius is. I keep that number in my calculator. I cube it. I take it to the power of 3. That should be a little 3 there at the top. And then I work it out from the calculator to get 3,600 cubic centimeters. That's to two significant places because those last two zeros are not significant. You might be asked to give that in liters, and then it's always a good thing to remember that 1,000 cubic centimeters is equal to 1 liter. So in fact the soccer ball contains about 3.6 liters of air. Good thing to remember, I suppose, if you want to blow one up. Let's take a small break, and then we come back with our new topic for this program, and that is about geometry. The second part of this program concerns introduction to geometry. There are some terms, there are some definitions that you have to know about. Let's make a start. We start in geometry always with a point. Now that has no size and you cannot move it. It's generally indicated by a capital letter. And if you have two of those points, you can connect them up by means of what's called a line. And you notice the symbol there at the top. It can be a ray as well. Now a ray starts at one point and then goes through the second one and goes on indefinitely. Or it can be a line segment where you start at one point and finishes at another. Now officially you should use that notation above that AB, but very few people take much notice of it. Euclidean geometry, as this is called, isn't taught as much in schools as it used to be. But if you want to become an engineering draftsperson, you have to know about geometry. Any of these packages you might use, like your computer-aided drafting, will have geometry in it. There's also another notation, and that is AB without anything on the top, and that then simply means the length of the line segment AB. Now an angle is simply a pair of rays that have a common endpoint. In this case, the common endpoint is A. And the notation for that is, in this case, BAC. That A is there in the middle. You start at B, you could say, you go through A and you go through C at the end there. Angles are always measured in degrees in this subject. In higher mathematics we use radians, but in engineering, civil engineering mathematics A, we use degrees. And you can actually give different names to different types of angles using degrees. A full revolution is 360 degrees, and that's the notation there with that little 0 there at the top. We look at the angles now and the different names. An acute angle, that is one that is less than 90 degrees. A right angle is 90 degrees, and you always use this symbol there for a right angle. We've got an obtuse angle that must be greater than 90 but less than 180, and we finish off with a straight angle, which is 180. And there's one that is not used a lot, that's actually called a reflex angle. That is when the angle is greater than 180, and you have to go into this motion there to make a difference between a reflex angle and an acute angle. Then there are different types of angle pairs that are important in geometry. The first is the adjacent angle pair. If two angles are next to each other, they're called adjacent. You've got so-called complementary angles. They add up to 90 degrees. We've also got supplementary. They add up to 180. I can always remember why supplementary refers to 180, because S is later in the alphabet than C. C is earlier on, so that must refer to the 90. S later on in the alphabet, so it must refer to the 180, something more. We also got vertically opposite angles, and they are actually the same in size. That can be proven quite easily. When you have two parallel lines cut by a third line called a transversal, you create a lot more angle pairs, and I've got those listed here. You've got so-called corresponding angles. They're in corresponding positions, as you can see. There are alternate angles. They are on the different sides of the transversal. And there are so-called co-interior angles. You just have to be familiar with that terminology, I'm afraid. A lot of things to remember in geometry, and I'm going very fast through it. You have to check in your book, of course, and to make sure that you know these terms. But you can actually do some arithmetic with angles and add up different angle sizes. And if you have a calculator, then that becomes quite easy, because most calculators have a button, a degree, minute, second button. Let's first of all go through what a degree actually is. As I already mentioned it, it's 1/360th of a full revolution, and in fact a degree you can subdivide into 60 minutes. And the notation for a minute is just an apostrophe over there. 1 minute again is 60 seconds, the same as what you use with time, and you've got a double apostrophe there for seconds. Nowadays angles are frequently expressed in decimal degrees, so I can say 30.5 degrees. Now you have to be able to add up angle sizes, subtract them, and sometimes even multiply them. Again, if you've got a calculator, that becomes quite easy. Not many students know, however, how to use that button on the calculator. Have a look at your instruction booklet and see if you can do the problems I'm doing here on the screen by means of the calculator. First problem, find the complement of 35 degrees 15 minutes. Well, the complement, you have to find the angle that makes the total 90 degrees. In other words, you have to subtract 35 degrees 15 minutes from 90 degrees. That is not possible because I haven't got any minutes there, so I change 90 degrees to 89 degrees and 60 minutes. Now I can do the subtraction. 54 degrees, 45 minutes. Second problem, find the supplement of 107.89. That is in decimal degrees. That should be easy. That is 72.11 degrees, decimal degrees. The next problem is a little bit more difficult. It can be done on the calculator. Let's have a look at it. Here we have to add two angles. Now if we add 23 to 59, that will bring us over the 60 seconds. And in fact it becomes 82 seconds. And you can't have 82 seconds, it becomes 60 seconds is 1 minute. So the 57 will be increased by 1, becomes 58. And because 82 is of course 60 plus 22, you end up with 22 seconds there. Subtraction for this problem is actually quite difficult, easily done on a calculator, mind you, but here we go, because you have to borrow, Let's have a look. The subtraction, you can't take 59 from 23, so you have to make the 23, you have to make it 83. Then you have to borrow again. In fact, you have to borrow twice. When you do that, in the end, you end up with 4 degrees, 32 minutes and 24 seconds. It's always easy to check by adding the 4 degrees to the 17 to get that answer over there. The last problem in this section, again, a calculator can convert very easily between degrees, minutes and seconds and decimal degrees. If you have to do it by hand, a little bit more difficult. You have to change 22 degrees, 15 minutes, 23 seconds to decimal degrees. One way of doing that is to realize that there are 60 minutes in a degree, so 15 minutes is 15/60th of a degree, and also there are 3,600 seconds in every degree, so that 23 seconds becomes 23 over 3,600. Do it all in the calculator to 4 decimal places, that comes to 22.2564. The other way around, change that to degrees, minutes and seconds. Well, 17 you don't have to touch because that's already there, so you look at the remainder part, multiply that by 60, and that gives you 52.5. That's close to 53 minutes, and so the answer should become 17 degrees and 53 minutes. We're nearing the end of program 2. There are just a couple of typical geometry problems to follow. One type of typical geometry problem is to work out an angle that is not known initially. Typical problem here, let's have a look. We've got a straight line divided into 3 angles there. So we know that the total is 180. We already know that is 40, that's 57, so we can add that up, take it away from 180, and I get 83. Now I haven't put the degree sign there because that variable x already has the degree there. Let's have a look at another problem. Here we've got 2 parallel lines there. We know that that particular angle there, y, must be 44 degrees because it is in the same position as that 44 degrees there. Then we can work out what x is going to be, because that is simply the difference between 180 and the sum of those 2 angles. Now we look at constructions. There are many different types of important constructions in engineering, but I haven't got the time to go through all of those. I can only give you one example. I'm going to bisect an angle. Now how do you do that? If you put your compass on point C and you draw an arc, you create 2 points A and B. Then you put your compass point again on A and B, create an arc here and an arc over there to get to point D. And then the final step is to connect C with D, and you've got the angle bisected. As I've mentioned, there are many more standard constructions, and you have to be familiar with them. You have to read through the book and master those. Now, what have we covered in this particular lesson? We did area calculations first, then we did some volume calculations. We looked at the definitions in geometry. We did some adding and subtracting of angles. And then we found unknown angles, and finally we did a construction. You have to practice that in your book. Lots of exercises there. Chapter 3 deals with areas and volumes, and Chapter 4 deals with Introduction to Geometry. This brings to end program 2. I hope you found it interesting and enjoyable. In program 3 we continue with geometry. I'm looking forward to your company then. Bye for now.